talked about section 10.1 last time, correct? Yeah. What do you want to look at? There's probably some good ones in those like 20 range. Yeah. Rita? Sure. This first set, I think we could do like all the way up to like 40. And Rita, you said which one?
27.
27, okay. All right. So there were some more directions to this problem, right? They ask you to eliminate the parameter and then find the domain and range. We're going to skip the eliminating the parameter piece because of request. Is everybody okay with that? When we do that, you would have gotten x squared plus y squared equals 5 squared. So for the domain, what we're going to be looking at is 5 cosine t, right? Because that's the x variable. And I noticed that t is covering 0 to 2 pi. So it covers the entire domain of cosine, of the cosine function, right? Over that domain for cosine, what is the biggest and smallest value that cosine can take? We talked about it first semester. That's okay. What does the graph of cosine look like? Just cosine, forget about the 5. It looks like that, right, over its domain, where this is like 0, 1, and this is like pi negative 1, right? So the biggest value cosine can have is 1, and the smallest value is negative 1. So that tells me that the biggest value that x can have is 5 times 1, or 5, and the smallest value you can have is 5 times negative 1, negative 5. If I do the same thing with the range, well, the range is going to come from the y-coordinate, and that function is 5 sine t, and the t's go from 0 to 2 pi. If I think back, 0 to 2 pi is the entire domain for sine. What is the biggest and smallest value that the sine function can take over its domain? Negative 1 and positive 1. Same thing, right? Because if I think about the graph of sine, what does it look like? Looks like that, right? Where this is like pi over 2, 1. This is like 3 pi over 2, negative 1. So the same thing is happening. The smallest value we can have is negative 1, and so we have negative 1 times 5. And the biggest value you have is positive 1, 5 times positive 1. So there's our domain and range. Does that feel okay?
Yeah.
So here I used what I knew about sine and cosine function and their domains and ranges to really answer this question, right? So this was a little bit more thinking about it question than an algebra-based question. And in a way, because we remembered all that stuff from first semester, it was easier than a lot of the previous ones would have been, right? Because there's not a lot of extra complicated stuff going on. It's just like, oh, okay. I already really know a lot about these guys. Who's next? Happy to do some more? Rita, go ahead.
Should we also do 38?
Sure. All right. So here we're looking for the parameterization. So we want our f of t function. Okay. So let's go back and just look at this previous problem right here. When we graphed this, what did we get? We got a circle centered at the origin with radius 5, right? So here we want to write the parametric equation for a circle whose center is the origin and whose radius is 2 root 3. So I'll just follow the same model that I had on that previous one. Just that. And I'll make the t the same thing as that problem, and it should be what I'm looking for. If I want, I can always go back and check this after I'm done to make sure that I'm getting what I'm expecting. But there's not a whole lot to do there. Yeah, well, I mean, it's one of these, you're just learning it. So it's like, oh, is that all I have to do? That maybe doesn't seem totally obvious that that's all you would need to do. So, you know, that's why we have question time, right? And if you already knew it, you wouldn't need me. You know what I mean? We can't do everything in the lectures, so like if there's still stuff that's kind of like dangling as a question, that's okay. And our t should be 0 to 2 pi. And uh-oh, syntax. What's the problem there? I don't know. I meant to do this, first of all, Mr. Kulik. But I don't think that should be the problem. Okay. Let me try it again. Syntax. What's the syntax error, guys? Oh, I have some extra stuff going on in here that I didn't mean to. Well, there's some stuff in there that was like off the screen. Okay. Syntax. What's the, where's my, okay. All right. You just, calculator trying to outsmart me here. Okay. All right. Try it one more time. There you go. Goodness gracious. Where's the other half? Oh, I know why. Because, no, I am in radians. What the... Why didn't it give me a full circle? I just don't know what's going on with my calculator right now. This is giving me weird outputs. I'm going from 0 to 2 pi. That's fine. My window's whatever. That's okay. This is 2 root 3 times cosine t, and 2 root 3 times sine t. That should be fine. Well, heck, I don't know. Let's try this. Why is it being... Oh, I see. Okay. Okay, just being silly. maybe. No, it is literally just doing half of it. Why is it only doing half of it? Well, that just doesn't make any sense to me, why my calculator is being so obtuse right now. Let me check something real quick. I'm sorry for taking so long on this silly question. Well, I guess it's not silly if I'm having such a problem with it. Yeah, that's exactly the right answer. Why is the calculator not cooperating here? I give up. Oh, maybe this? Let's try that. Now, give me a break. What was wrong with that? Okay. There. I'm stumped as to what my calculator's malfunction is. This is the correct answer. That is all you need to do. Why my calculator's not giving me anything that seems reasonable, I just don't know. Why are you being dumb, calculator? I mean, this shouldn't matter. Yeah, I'm stumped, Rita. I don't know what the calculator's doing. That's the correct answer, though.
Thank you.
Yeah, I mean, I don't know. I don't know what to tell you. Okay. You got another one?
No.
Are you sure?
Yeah. Or, I mean,
Go ahead. It's okay.
like, for 33, like, when I, like, checked it, like, it seemed like work for, like, the interval.
Okay.
So, like, I don't know. I couldn't figure out what it was.
Okay, well, let's do 33 real quick. That's okay. That's what this time is for, right?
Yeah.
It'll be all right. 33. You're making faces. I could tell you didn't want to really be done. All right. So we had talked about this last time, that the best way to do this was to treat this as like a vector line equation. So let's start by creating my vector v. And it doesn't matter which one, whether you do head minus tail or tail minus head, it's just like you subtract the two coordinates and it's going to be fine. So that's -4, 7. So my vector r is going to just be like -1, 5 plus -4, 7 t, or -1 minus 4t, and then 5 plus 7t. So that's going to be my parameterization. And the nice part about this is I know what my interval is going to be. It's just going to be one or the other. 0 to 1 or -1 to 0. I just have to check. So if I say I do f of 0, I'm going to get -1, 5. Well, that's good. If I do f of 1, I'm going to get, what I get? I get -5, 12. That's bad, because that's not one of my 2 points. So my answer must be -1, 0. Just to confirm that, if I do f of -1, I'm going to get 3, -2, which is what I should have been getting.
Yeah. And that answer is 0, 1.
Oh, well, it depends on how you write the equation. If your equation is a different parameterization, then your interval could be different. So like answers may vary here. It depends on like which V you come up with. If you come up with the opposite sign V, then the parameter is going to be different. So just because your answer might not match like this, there's lots of possible answers. Yeah, it's a good thing to check and talk about, right? Yeah, so we didn't list all possible answers here. We just listed one such possible answer. And obviously, like, it's not the only one. Now we know. Prater. Sure. Okay.
Thank you.
You're welcome. Does anybody else have anything that you want to talk about? Okie dokies, let's start this party here. So today we're going to be talking about, let me find it, an application of parametric equations, that being parametric motion. So, anybody in physics right now? A couple of us. This will seem familiar if you are, because if you did two-dimensional kinematics, which I suspect you've done by now, this will look familiar. So this is so from a height s in feet and vertical velocity v in feet per second of an object in free fall, ignoring air resistance, after t seconds, are given by the equations. So S is for the height of the figure. This is something that's like being dropped. It's only moving in one dimension, just like up and down. So our position function is S of t equals 1/2 gt squared plus v naught t plus s naught. So g is the gravity. That's constant, well, at least on Earth, at least at sea level. The greater the elevation, the lesser gravity is. You might have guessed this since you go up in the air and eventually gravity stops, right? S naught and V naught represent the initial height and velocity of the object. So the velocity and position where the object is at time 0. So if we're doing a one-dimensional problem like this, there's really no need to really parameterize anything. We can just use these equations, and again, those of you that are in physics, those guys should look pretty familiar. So it says a ship is stranded in the ocean. On the top of the bridge, 80 feet above the water, a distress flare is shot straight up with an initial velocity of 72 feet per second. Provide a graph of the flare's height against time and find the height of the flare above the water after 1, 2, 4, and 5 seconds. Okay. So we'll just draw a little picture here. Ooh, there's some water. There's my boat. And we're shooting the flare up. So just kind of coming up and then coming down, right? Okay. So we are interested in height against time. So writing an S of t function. So that, according to my definition up here, is negative 16t squared plus the initial velocity plus the initial height Everybody's okay with that? It says then to plot a height or graph a height against time. So I'm going to just switch back to, well, I guess we could still do this in parametric. We'll just make the x-axis time, t, and the y-coordinate will be this negative 16 t squared plus 72t plus 80. And I'm going to go set my window. Since the t is time, makes no second sense to talk about negative time, right? And I don't know how long it'll take the flare to go up and then come back down, but 10 seconds ought to cover it. That'd be a real high flare. The x, again, since the x is just t, I'll just go that 0 to 10. And the y is going to be the height. So that's going to get pretty tall, right? Because it's at least starting at least 80. So I don't know what I'm going to do this at. Maybe like 200 or something. And then I'm going to hit a graph. Oops. I turned my axes off there. Let's turn that back on. Okay. So there's that. So if I want my value at 1 second, it's 136. So second trace, pick that value again. If I want the height at 2 seconds, just pick 2 and enter. That's 160. Second trace, value at 4 seconds, that'll be 112. And then second trace value, that'll be 5 seconds. And that's 40. Yes? Sure. So I did 0 to 10, 0 to 10, and 0 to 200. Sure. Now, if we look at this graph, though, does this actually represent the motion of our flare? Does the flare like go out and then down? What if we wanted just a position function where it was graphing the actual motion the flare does? So if we use our parametric equation, the x-coordinate now should be a constant, right? So let's just pick a constant to represent the position of the ship. I'm going to pick 1. Why didn't I pick 0? Because the y-axis would be in the way. I wouldn't really be able to see anything. I'm just going to pick 1 because it'll do that. And I'm going to change the way this is going to graph. So instead of just giving me a straight line, I'm going to move, oops. And I'm going to pick this one that's like the little circle. Now everybody watch when I hit graph. That's what the flare did. That's nice, right? That's pretty cool that I can do that with my calculator. So that open circle just traces it, what the function is doing. If I had gone through and did the circle with the line after it, let's do that one real quick. It does the same thing, but it traces the path behind it. So you can see it kind of draw it in real time. Now, this graph is a good position graph, but can I do this? Could I write an equation in Cartesian form to do this? No, right? Because this is a vertical line, right? I can't write a function for this. Specifically because I can't write the vertical line to stop at some point, right? Like it has to go to it and then stop going up. Whoa, boy. So that's a nice representation, right? What if we actually have projectile motion, like assume the flare wasn't shot straight up, but was like shot at an angle? Pew. And we actually get something that's parabolic. Can I write the equation for that type of motion? Physics students, you know what's coming. The answer is yeah, of course you can. So let's talk about that. So an object in projectile motion, that's where it's shot, not just straight up and down, but like also left and right a little bit, with an initial angle theta taken from the horizontal. What does that mean? That means if like this is our cannon, pew, and it shoots something, right? That the angle that we're looking at, actually, like from the center of the cannon, would be like, oops, that angle, right, with the horizontal. And just talking about how we're measuring the angle, right? So what can we say about that angle, that initial angle? It always has to be acute, right? If it's taken to the horizontal, if you get past the other side, then the horizontal's on the other direction, you know, so. And the initial velocity is the magnitude of this vector v, where that vector is just the magnitude of the velocity times cosine theta, comma, magnitude of the velocity times sine theta. So it's basically talking about the horizontal component of velocity and then the vertical component of our velocity, right? Okay. So the distance x and the height y in feet, and then the horizontal velocity vx and vertical velocity vy, all in feet per second, of the object after t second are given by these equations, where s naught is the initial height of the object when the time is 0. Okay, so let's look at the kinds of problems that we can answer with this type of, or with these types of equations. Physics peoples, do these look familiar? These motion equations that were given you guys? They ought to, or else you might have been dozing that day or that month. It was probably about a month of 2D motion. All right, let's look at this example. You hit a baseball that's 3 feet above the ground with an initial speed of 135 feet per second and an angle of 16 degrees above the horizontal. Will the ball clear a 15-foot fence that is 300 feet away? If yes, by how many feet? If no, how high up the wall will the ball hit? So just to like draw a picture of our situation here. So there's our setup, and we want to know, like, does the ball hit the wall, and then how high? Or if the ball clears the wall, by how much, right? Everybody's cool? All right. So let's start by writing our position, or our parametric equation. Are we interested in positions or velocities here? What's the question asking? It's talking about where will the ball be, right? Rather than how fast it's going. Everybody agree? So this is a position function. So the x of t is that initial velocity times cosine of 16 degrees times t. The y is negative 16t squared plus that initial velocity times sine of our angle t plus the initial height, which is 3. So let's just kind of type this into our calculator and take a look at the picture, right? We'll start by doing that. So 135 cosine 16 times t. Ooh, what else am I going to have to remember to do here, guys? Before I hit graph. Yeah, there you go. That's using your noodle. Yeah. Notice the angles here were given in degrees. I certainly think I was in radians because I was just in the mode menu just a few minutes ago checking that out. So I'll do that. Okay, baseball players in the room. How long, you got like a pop fly or a line drive, how long that ball going to be in the air? Just like ballpark it for me. Like 10 seconds is clearly absurd, right? You have 10 seconds of ball in the air. 5 maybe? Okay, that seems okay. And then I know that the initial x is 0, right? And we're going at least 300 feet. So I'll make that like 350 or something. And I don't know, go by 50s or something. And the y-min, again, 0. And I don't know how high up that thing's going to go. 16 degrees is a pretty low angle of exit, though, right? Baseball players, that's fairly line drivey. Don't you guys think? Yeah, so maybe that's probably like, I don't know, 50 or something feet might be as tall as that thing gets. 16 degrees that ain't much. Everybody okay with that? So I'm just kind of guessing at this. If your picture looks crummy, you can always go back and change your window, but we're just kind of ballparking it. Okay. So that's the path the ball takes. Now, wouldn't it be nice to be able to graph the wall in here too, so we can actually see visually what's supposed to be happening here? That'd be pretty cool, wouldn't it? Guess what? We can do that. What? All right, let's do it. Let me show you how we do this. So where is the wall at, the position of the wall? 300, right? And then how tall is the wall? 15. And what I'm going to do is divide that by T max. So that's a variable, right? That was one of the window variables. So I'm going to press vars. I'm going to pick the window option. And I'm going to go over to the T/theta option. And I'm going to grab T max. And then I'm going to multiply that by T. So what is T dividing by T max and multiplying by T going to do? That's going to cover all the fractions between 0 and 1, right? Because T max is fixed at 5 or whatever. And then T is going to take all the values between 0 and 5, right? So what are we going to get? You're going to get a line that starts at 0 and goes up to, well, 1 times 15, so 15 feet. And then I'm going to turn this one up here now into the tracer. Okay. All right. Oh no, it's going to do that, isn't it? All right, well, I'll do it with the drawing tracer. So it's going to graph this one first and then this one second. Let's do this maybe. If I do that, that'll draw it in first. And then if I come back, there it goes. So what do you guys notice? Doesn't make it over the wall, right? And we can see that clearly visually just by clever use of our calculator. Now, can we tell where it hits the wall at by just using our calculator? I don't think so. But we can do this algebraically pretty easy. So let's think about what we want, right? We want the height of the ball when the x-coordinate is 300, correct? What do you need to calculate the height of the ball, period, any place? You need a value for t, right? Because you have to, it's a function y of t. So what we're going to do is we're going to plug 300, or set x of t equal to 300, to find the t at that position, and then plug that t into y to get our answer. So 300 is going to equal 135 cosine 16 times t. Or I'll just divide both sides by 135 cosine 16. And I'm going to use my fraction command on this one because it's really easy to goof up those parentheses. You need to use a parenthesis in the denominator there. But rather than mucking around with that, I can just type it in my calculator exactly like it looks. So I get about 2.31 seconds. So if I do y of 2.31, sure, that should give me my answer, right? So I do y1 of, making sure I chose from the parametric menu this time, that number or you could have just plugged it in manually. That would have been okay too, right? But this is the same thing we've done before where I just did vars, y vars, and this time I chose from the parametric menu since we're in parametric mode, and that's where my parametric equation is stored. And I did y1t because that's where the y component for the motion of my baseball was stored. So y1 of that number gave me 3.51. So what do we say? No, the ball hits the wall 3.51 feet above the ground. Or was it a fence? Whatever. It was something. Wall, fence, obstruction, force field. I don't know. It was something. You want to do another? So again, this should be like the actual process of doing these should be pretty clear as to kind of what to do if you're thinking about it as like, okay, this is just the horizontal component and this part's just the vertical component. All right, so let's read this one, this similar idea. So Jeff hits a baseball at 3.5 feet above the ground. Jeff's a little taller or something here. With an initial speed of 141 feet per second, an angle of 14 degrees above the horizontal. Will the ball clear a 20-foot fence that's 400 feet away? Yes or no? If yes, by how many feet? If no, how high up the wall will the ball hit? So just like before, let's start by updating our calculator and getting a picture of what's going on. So I'll update the angle to 24, the speed to 141. And then the height, initial height of the ball has to be updated to 3.5. And here the fence is 400 feet away and 20 feet tall. Just really gonna have to do a number on this to get it over there. Everybody's cool with the setup so far? We're going to have to change our window though, right? So this ball's hit a little bit higher angle, a little bit further. Maybe I'll update my T to be maybe 7 seconds, maybe allow for a little bit more time in the air since it's hit a little bit more upward. Definitely need to change my X max because my wall is now 400 feet away, so let's make that 450. And I definitely need to change my Y max because this ball's hit, much further up. So maybe I'll just make that 100. I don't know. This feels like a little bit more of a home run shot than that line drive we hit before. Let's hit graph and see what we get. There's Jeff. And there's the wall. He did it! Dingers, right, guys? I changed that, didn't I? Okay, good, I did. Okay, so we got a home run situation here. Let's figure out how much we cleared the fence by. Is this going to be any different of a problem than we just did? No, approach it the exact same way, right? So we're going to take 141 cosine 24 and set that equal to 400. Oops, t. So t should be 400 divided by 141 cosine 24. I'll just see what that is real quick. So about 3.11 seconds. So then I'm just going to do y of 3.11. So to get the y1 for the parametric, I press vars, go over to y vars, I pick parametric, and I pick x1t of that number, and I get 27.3. Since the fence was 20 feet tall, we cleared the fence by 7.3 feet. Okay. Everybody feel okay there? Let's take the same situation. This is still Jeff hitting his baseball. What if we change our question, though? Still Jeff's home run swing here. But assume there's no obstructions, and we want to find how far will that ball travel before it hits the ground. So here, what component are we looking for, an x or a y? An x, because we're looking about how far it's gone. Great. So we're going to have to be solving then using the y component for t, correct? What is the y? What is the height of the ball that we're interested in? Yeah, hits the ground. That means the height should be 0, right? Okay. How do I solve an equation like this for 0? It's a last year question, guys. It's making me a little nervous that nobody's blurted out the answer yet. Quadratic formula, right? Okay, who remembers the equation for the quadratic formula? Negative b, so my b is 141 sine 24 plus or minus the square root of b squared, so 141 sine 24. Notice that I am writing that in parentheses. That parentheses around it must be there. Minus 4 times AC divided by 2A. All right. I'm going to type that all into my calculator exactly as it's written there. Well, except I'm going to need 2 lines because I have to do one for a plus and one for a minus. So alpha y equals fraction command negative 141 sine 24 plus square root parenthesis 141 sine 24 close the parenthesis squared minus 4 times negative 4 times 3.5. Negative 4 times negative 4, Mr. Kulik. What are you doing? I don't know. Making mistakes. There's supposed to be negative 16 there. Excuse me. Divide by 2 times negative 16. So I think I got it all in there. Negative? Why? That doesn't make any sense, does it? Think about our picture. All we found is like this spot over here, right? Oh, well, yeah, that would have to be a negative because we started 3.5 feet above the ground. So like some negative fraction of a second, the other side of the, yeah, okay. Well, that's clearly worthless to us. We don't care about that number. So we'll go back and change that and make it the minus then 3.64, which makes sense to us, right? Because how long was it? How long did it take to get over the fence? Like 3.1 or something, right? So another half second in the air. I'll buy that. And then we just want x of that number. So again, I'll go back to my calculator. Vars, y vars, parametric, and then x1t was where I left that. So do x1t of that number. So I get 469.4. Jeff's a beast. I want him on my team. Okay, so far so good. All right, let's ask one more variation on this same situation. Jeff is still our home run king here. Assuming that there's no other obstructions in the way, what is the furthest distance away from that starting position you could place a 20-foot fence and still have the baseball clear the fence? Right, so we noticed, okay, well, Jeff hits a home run when it's 400 feet away, right? We've seen that. And if there's no fence at all, the ball lands 469. Somewhere in between there, though, you could have probably backed that fence up some and still had a home run because we cleared the fence by 7 feet. That's kind of a lot. So here, what are we asking for? Are we asking for a height or a distance? Are we asking for an x component or y component? It's asking for an x component, right? How far away could that fence be placed? So we're going to be solving y of t for t and then plugging that t back into x, right? The question becomes, what value are we solving y of t for? Well, what height does the ball have to be to make it over the fence? 20 feet. So we're solving y of t equals to 20. So this is our equation that we're solving. What do I have to do to solve this? I got to do something first. No. It's got to be equal to 0. Yeah, so we just subtract the 20 from both sides. You guys knew that. You're just messing with me. Actually, it's Monday morning. Maybe you didn't know it on Monday morning. If I asked you like an hour later, you would have known it, though, I'm sure. So we do that, and then we, have our quadratic formula, just like before. The only difference here is that now our C is a new number. That's okay. Everything else is still the same. And because everything else is still the same, that's going to make it nice for me putting it into my calculator, right? Because guess what Mr. Kulik's going to do? I'm just going to go retrieve that last one and just change that to negative 16.5. That's pretty nice. So I get 3.85 seconds. What? I think I forgot to make that negative. Yup. Why did Mr. Kulik know there's something wrong there? Because 3.85 was bigger than 3.64, right? That certainly couldn't be the case. And I forgot to put the negative on my 16. There we go. 327. That seems about right. That's in between the 311 we got when we were just looking at the fence 400 feet away, and the 364 that we saw when there was no fence at all. So now we do this. So again, vars, y vars, parametric, and we want y. Not y, dum-dum. You wanted x. Yikes. It's Monday morning for Mr. Kulik, too. And you got about 421.1. Ooh. Here's a question. Should we be rounding? We got to be careful here on rounding this, right? Which way should I be rounding? You have to round down, right? Because if you back the fence up too far, it's going to hit the very tippy top of that, right? For rounding, it's got to turn into like this guy. Now, I don't know that I would be that picky about that on a test or whatever, but we'll talk about being picky about it now because, this is the time to talk about being picky when it doesn't really matter. Everybody feel okay there? So that's basically the gist of it. You guys should be able to do up to 48 now. And what's the weekend? The 12th, I think, is Sunday. So we'll add that to Sunday's problem set. And if I were you guys, I would want to be up to speed on this stuff probably by next class, because you might have one of those things that happens every chapter on the next class. Well, it's better than waiting like 5 days and then doing it like after you've been gone from school for like 5 days with the long asynchronous days or whatever. I mean, you can make your faces, but at least I'm giving you the heads up, right? Everybody okay? Other than like finding out that there's a homework, or hinted at there's a homework quiz, right? Because I didn't tell you, I just hinted. And that's always yucky, but I think this is a good place to stop. I don't want to get into the next thing with 15 minutes left. That seems dumb. Why don't you guys get your stuff out and get a jump on? You can probably get through a problem or two, and it'll be nice reinforcement to get that right after you've seen how to do these guys.